Welcome viewers. Today we will study organic synthesis via enolates. By this topic, we will study large number of the compounds which were otherwise very difficult to form. But before we study, we must know about the terms enolates, and before enolates, we should know about the acidity of alpha hydrogens. Let us study the acidity of alpha hydrogen and formation of enolate. Now, aldehydes and ketone constitute two isomeric series of compound, both of which contain the carbonyl group in their molecules, and they are therefore collectively known as carbonyl compounds. Like aldehydes and ketones, both contain carbonyl group. These carbonyl group, besides providing a site for nucleophilic addition to aldehyde and ketones, the carbonyl group is also responsible for the acidity of alpha carbon atoms. The carbon atom adjacent to carbonyl group is known as alpha carbon atoms, and hydrogens attached to alpha carbon atoms are known as alpha hydrogens. These alpha hydrogens, when these are attached with this carbonyl group, this carbonyl group acts as electron withdrawing group. This attracts the electron from this carbon-carbon bond towards itself and makes this carbon alpha carbon electron deficient. This alpha carbon atom in turn attracts the electron from this CH bond, thereby decreasing the electron density and making this H weakly attached. This H, when it is treated with the base, it is removed in the form of proton. This is the acidic nature of alpha hydrogen. This alpha hydrogen is also present in simple alkane, but there the pKa value of alkane is 40, and in case of aldehydes or ketone, this pKa value is 19. What is pKa? pKa is the negative logarithm of Ka. Ka is the dissociation constant for the acids. Higher is the Ka, stronger is the acid. But here lower is the pKa, stronger is the acid. Now, in case of alpha hydrogen, the pKa value is 19. But similar type of the bond when present in alkane, its pKa value is 40, much less acidic than the protons and much less acidic, and this is much less acidic than the protons of carboxylic acid. It can be removed as a proton by strong base, and the anion formed after the removal of proton is called enolate anion. It is stabilized by resonance. Now, it is stabilized by the two structure, by one structure. In the one structure, it is favored because of carbon and oxygen double bond. Because the energy of carbon oxygen double bond is 364 kilojoules as compared to the carbon and carbon double bond in the structure 2, whereas its energy is 251 kilojoules. But structure 2 contributes more towards the resonance. Why it contributes more towards the resonance? Because in this case the negative charge is carried by oxygen, and in the structure 1 the negative charge was carried by carbon. These two contribute towards the resonance, and these are equivalent to the third structure, which is known as the enolate anion. Now, the enolate anions, they can be protonated by the addition of proton. When we add proton, it can be added at the carbon atom, and when it is added at the carbon atom, it yields the original form, that is keto form, and when we add the proton at oxygen, it yields a enol form. Keto form, enol form. Aldehyde and ketones, though these are unusually acidic in nature, but these are weaker acidic in nature. When we treat them with the sodium hydroxide, they get converted into enolate anions and water is formed. In the second case, ethyl acetate, when it is treated with the base like sodium alkoxide, it is also converted into enolate anion and ethanol is formed. In both the cases, in the product side, in the first reaction, water is formed and water has a pKa value 15. This is stronger acidic in nature as compared to the acetone. So, the reaction moves in the backward direction. And in the second case, again ethanol is formed and it has a pKa value 16. In the second case also, the reaction moves in the backward direction. So, when the aldehyde and for simple aldehyde and ketones, the amount of enolate anion is very less. It can be increased if we use strong base like soda amide. When strong base like soda amide is used for the removal of alpha hydrogen, this gets converted into anion and ammonia, and ammonia has a pKa value 35, whereas pKa value of alpha hydrogen here is 25. This is weaker, so reaction cannot move in the backward direction, reaction moves only in the forward direction. The simple esters and ketones are very weak acids with pKa nearly 20. However, when a CH2 group is flanked by two carbonyl groups, then these alpha hydrogens become considerably acidic in nature with pKa nearly 10 than an ordinary carbonyl compound. Because of the more resonance stabilization of the resulting anion by the additional carbonyl group in acetyl acetone, this CH2 group is flanked on either side by two carbonyl groups, which makes this alpha hydrogen more acidic in nature, and when this is treated with sodium ethoxide, it is converted into anion. This anion is stabilized through the resonating structure, electron shift like this way, and this structure is obtained. In the other side also, this negative charge is in conjugation on the other side also, so this second structure is produced. So, acetyl acetone is stabilized through these three resonating structure and it forms ethanol whose pKa value is 16, and the pKa value of acetyl acetone is 9. Lower is the pK value, stronger is the acid. So, this is stronger acid as compared to the ethanol, and the reaction moves in the forward direction. In case of carbonyl compound which were having only one carbonyl group, the alpha hydrogen is lesser acidic and it has the pKa value 25, like in this case. In the other case, acetone, the alpha hydrogen has the pKa value 20, but when this CH alpha hydrogens, they were flanked on either side by the two electron withdrawing group carbonyl group, the pKa value is reduced to 13. In the next, ethyl acetoacetate, again the alpha hydrogen which is flanked on either side by the carbonyl group, the pKa value is reduced to 11, and in case of acetyl acetone it is 9, and in case of cyanoacetate again the value of pK is 9, means here the alpha hydrogens, they are stronger acidic in nature. In addition to a carbonyl group, other strong electron withdrawing group also increase the acidic character of an alpha hydrogen. For example, the effect of successive replacement of hydrogen in acetonitrile by the cyano group increase the acidic character. In this case, when one H is replaced by a cyanide, pKa value is 25. And when the two H are replaced by cyanide, pKa value reduces to 11, means acidic character is increased. And when 3H are replaced by cyanide, the pKa value is reduced to 1, thereby showing that if we increase the electron withdrawing group, that increase the acidic strength of alpha hydrogen. To sum up the discussion on acidity of alpha hydrogen, it may be stated that the enolates derived from the dicarbonyl compounds such as malonic ester, pKa 13 and acetoacetic esters pKa 11 are easy to synthesize. The reason being that these esters are stronger acids than ethanol, pK is 16, and hence their enolates anion can be easily obtained in almost quantitative yield, reacting the ester with an equivalent amount of sodium ethoxide. These enolate anions in turn can act as nucleophiles in a large number of SN2 reactions of synthetic importance. Malonic ester or diethyl malonate is employed as important synthetic reagent in organic chemistry. The synthesis of various types of compound by using malonic ester is called malonic ester synthesis. In this malonic ester, this CH2 group, it is flanked on either side by the two ester groups, which makes this alpha hydrogen acidic in nature. Because of acidic nature, we can use this diethyl malonate for the synthesis of large number of the compounds. Its utility depends upon the following three reactions: formation of enolate anion, alkylation of the enolate anion, and hydrolysis and decarboxylation. First of all, we will take formation of enolate anion. When this diethyl malonate is treated with a base, it removes alpha hydrogen from this methylene group and gets converted into anion, and this anion is then stabilized through the various resonating structure like this, because negative charge is in combination with the carbonyl group. This is a structure. In a similar way, it shows the second resonating structure, or these resonating structures, they are equivalent to third structure in which negative charge is dispersed over all and they are having one and a half bond. Enolate anion of malonic ester is a strong nucleophile. Therefore, it readily undergoes SN2 reactions with unhindered primary alkyl halide to give high yields of alkylated products. Like in this case, when it attacks alkyl halide, X is replaced and this nucleophile is substituted and we get high yields of alkylated product. But when this nucleophile is treated with secondary alkyl halide like cyclohexyl bromide, it forms a product but the yield is low. And tertiary alkyl halides do not undergo substitution, rather they undergo elimination. And aryl halides, they cannot be used for alkylation because they do not undergo SN2 reactions. This alkylated product, it has still one more hydrogen which acts as acidic in nature. So, if it is treated with a strong base, it can be again removed and can be alkylated. Now, when it is treated with a strong base, it is converted into anion, and when this is treated with Rx alkyl halide, it is substituted by another alkyl group and forms dialkylated product. The monoalkyl and dialkyl malonic ester obtained above, upon hydrolysis with aqueous alkali followed by acidification, give the corresponding dicarboxylic acids, and these acids thermally unstable and yields monocarboxylic acid. Like in this example, this is the monoalkylated carboxylic acid, which upon hydrolysis produce salt of acid, and this upon acidification produce dicarboxylic acid, and when this is heated at 423 to 473 Kelvin, it undergoes decarboxylation and produces the compound monocarboxylic acid. In a similar way, dialkyl malonic ester can undergo hydrolysis, and upon hydrolysis, when this is acidified by dilute HCl, this produces dicarboxylic acid, and this dicarboxylic acid upon heating to 423 to 473 Kelvin loses carbon dioxide and forms a dialkylated monocarboxylic acid. So, the synthetic utility of malonic ester is due to presence of acidic alpha hydrogens, which can be easily removed by a suitable base to form resonating stabilized enolate anion, and this enolate anion acts as strongly nucleophilic in nature. The strongly nucleophilic enolate anion reacts with alkyl halide etc. to form substituted malonic ester by SN2 reactions. On hydrolysis, substituted malonic ester form dicarboxylic acid, which undergoes decarboxylation to form monocarboxylic acid. Let us revise the topic. For simple aldehyde and ketone, the alpha hydrogen is acidic in nature because of carbonyl group, and after the removal of proton, it is converted into the anion known as enolate anion, which is stabilized through the resonance. For simple aldehyde ketone, the concentration of enolate anion is low, as in the product side water and alcohol were formed which were more acidic than the reactant, but in case of dicarbonyl compound, the concentration of enolate can be increased, and these enolate anion also can act as the nucleophile, which can undergo nucleophilic substitution, and which further upon hydrolysis and decarboxylation produce different kind of acid. So, the synthetic utility of malonic ester now we will study in the next lecture. Thank you.